Welcome. We have solved some problems on the pump and now what we shall do in this particular lecture, we shall be looking into some more problems on the pumps. So, in this lecture we shall be learning about the estimations of the specific speed of a pump, the capacity and the head developed by the pump and the power required. First we come to this problem that we have to decide what type of problem should be used to pump kerosene at a rate of this and to produce a head of this much with a pumping speed of this. So, we have been given the capacity, the head developed by the pump and the rotational speed. So, we have to decide that what type of pump is to be used. Now, first what we do that we first find out the N, that is in RPS, that is rotation per second, and we are given the rotational per minute. From this we find an RPS and then we find the put the value of Q and the H, and we use this specific heat equation, this specific speed equation. We put all the values of whatever we have put in this particular thing, and we find this is the value of the small ns, and this small ns is then converted to capital Ns, because in the manufacturer's data generally the specific heat is given in terms of the capital Ns. So, we also learnt in our lecture that the how to convert the small ns into the capital Ns by multiplying by this particular factor, and we get this value of the specific speed. And now this particular table which is supplied by the manufacturer, we locate this particular value and we find this value is coming here between this 500 and 5000 2064, and for this we have the radial type of centrifugal pump. So, based on the value of the specific feed, we recommend the radial type of centrifugal pump for this particular application. So, this is a very straightforward manner of utilizing the value of the specific heat, specific speed, and which we are finding from the given data to decide the type of the pump. Next, we come to another problem. In this, we have a prototype dynamic pump with this impeller diameter 24 inches, which is designed to deliver 12,000 gallons per minute of water at a total head of 100 feet, and the operating speed is 850 rpm, and then we have to develop a 1/4, that means a 1/4 of the scale model is tested at this particular rpm. So, the rpm has now increased. The specific gravity of the fluid is taken to be this particular thing, and now we have been what are the corresponding capacities and the head for the model, that is the when we are making it 1/4 the size of the prototype, and then the overall efficiency is 84% for both the model and the prototype pumps. So, we have to find out the what is the horsepower required and what type of pump is to used in the operating conditions. So, we have to go over selection of the pump, we have to find out the horsepower of the pump, and we have to find out the capacity and the head developed by the model pump. For solution of this, first we write all the data that is given to us, and here we do what? We may convert this flow rate of the liquid from gallons per minute to cubic feet per second with this particular relationship between the cubic feet per second and the gallons per minute. And these are the various head for the prototype. This P here represents the prototype and M represents the model. For the model, we have been given the diameter of the impeller and the rotational speed, and we have to find out the capacity and the head. Now, they are dynamically similar. So, we use this particular equation to find out the capacity of the model pump. Here we have been given plug in the values of the NP, NM and the DP, DM and the QM. We plug in the values and we give this is at the as GPM, and this GPM is then converted using this particular relationship. We convert it to the cubic feet per second. So, what we find that for the model pump, the capacity has come down from 12,000 GPM to in the prototype to only 386 GPM, and Why? Because the speed has got increased and also the diameter impeller has got reduced. Next, what we do, we have to find out the head of the thing. So, again we go for the similarity analysis. So, this is similarity equation we get for the prototype and the model, and now we plug in the values for each of these and we find this is the value of the head that is developed by the model pump. Now, for the power requirement, what we do, we use this particular equation for using the overall efficiency, and we find this is the particular power required, that is the 361 HP, and here we are using this conversion factor of 1 HP in terms of feet pound per second. And for the model, again because we have found out the QM HM value for the model from the earlier parts, and we plug in the values here and we find this is the power consumption by the model. So, the power consumption has come down for the model from the value for the prototype pump. Now, to decide the pump, what we do, again we find the value of the NS, we plug in the values of the N in terms of RPM, Q in terms of the GPM, H in terms of feet, we get this value, and from this particular chart which we saw earlier, we find out that this NS comes in this range, and for this we are recommending the radial type centrifugal pump. So, this is how we are able to select the pump for this particular application for the model pump. In the next question, we have been given this performance curve, okay, and this is the HQ and the eta naught Q, that is the head versus capacity, and the overall efficiency versus capacity. On this x axis we are plotting the capacity, on this axis we are plotting the head, and on this axis we have the overall efficiency. And this is for a centrifugal pump having impeller diameter of 32 centimeter, and it operates at a rated speed of 1800 RPM. And this system will, the schematic of the pumping system is shown separately, I will show you, and it has been shown that the minor losses in the suction and delivery side of the pump may be obtained from this particular equation, where V is the average pipe velocity. Now, here is the particular system, we find that some liquid has to be pumped from this to this, and this is the pump here, and the difference between the levels is about 25 meter. So, we have to determine the system flow rate and what is the power necessary to drive this pump, and if we have geometrically similar pump is required to develop some other head, that is from 25 meter we want to increase the head to 50 meter, and the flow rate is this particular thing, then we have to estimate the impeller diameter of the pump. So, with this information what we put that all this data which are given for our system, we find that the length of the pipelines on the suction side is this, on the delivery side is this, and this is the diameter of the pipes on the suction side and the delivery side. So, these are given to us, the friction factor is given, this friction factor will be used to find out the major losses in the pipelines, and this is the value of the gamma. Now, what we do for solution, we put all the data given to us and we now apply the first law of thermodynamics or the Bernoulli's equation. And here we find that both these surfaces are exposed to the atmosphere, so that they are experiencing the atmospheric pressure, and again we are neglecting the rate of change of the levels in these two tanks. So, that is how we are putting this VA and BB equal to 0, and then we find this is the expression for the head developed by the pump. And here we put the expression for the major losses, because total loss may be taken to be the summation of the major loss and the minor loss. The major loss is found from this expression using the friction factor, and this is the expression given in the problem to find out the minor losses. In this velocity is the this q by a, and a is the pi by 4 d square. So, all these things we are knowing. So, what we do that we plug in the values of everything and we find this is how we are generating the expression for the system curve for the head versus the Q. And for this above equation we find that we put different values of Q and we find the different values of H, so that if we plot this H versus Q on this figure, what will do that this is the, here we are plotting this H versus Q, and once we plot it, the point of intersection is giving us the particular system Q, and the brake horsepower can be, once we have found the Q value, then we can also find the value of the H, which is here is 54 meter, and then we plug in the values over here to find out the brake power of the pump, which is coming to about 79 watt. Now, what we do that locus of for the similarity pump, because in the second part we have been given that we are going to change the pump. So, we are putting this particular expression for the similar pumps, and that is H equal to some C Q to the power 2 by 3, and this C value can be determined from the value of the H and the Q for the new pump. So, we plug in the values and we find this is the value of the C, and now we can generate some value of the H and Q to plot, and again we plot these values and we find that this is the locus of similarity, and we find that wherever this we plot in this point of intersection of two curves, point 1 is similar to point 2, and point 2 is what? Point 2 is the one which is for the original pump. So, this similarity will be applicable for both the pumps. So, this we already knew from the first part, and this we find for this particular second part, and this particular Q1 and Q2 we can see that for when we are talking about similar pumps, both the CQ and CH will be the same, and CQ is given by this expression, and we put in this expression we find that N1 and N2 are the same, because in the problem they are saying that the pumps are running at the same speed. Once they are at the same speed, then this is the thing we find how the capacity is related to the impeller diameter, and this Q1, Q2 are read from this particular graph. We plug in the values of Q1 and Q2 and we find out the value of the impeller diameter for the second pump. Now, you may either use the equality of CQ, you may also use the equality of CH. Both should lead to the same answer. So, we can check that also, that we can do that. We put this equality of CH and we get this expression, and from this expression again we find that because N1 is equal to N2, so this head are related to the impeller diameters like this, and again we plot it. Now, instead of reading the Q, we are reading the H values. Once we read the H values from this graph, and then we know the value of D1, and again we find the value of D2, and we find that D2 is coming same as the one we just obtained by equalizing the CQ. So, I have just demonstrated that both the ways one can find out the impeller diameter of the other pump. So, in any one of them will suffice. So, these are the various references in which you can find more detail about these pumps. Thank you.